So, Namaskar, good afternoon to all of you, of all the participants around the world. I, Giriraj Methi, on behalf of Department of Mathematics and Statistics, Manipal University, Jaipur, hearty welcome all of you for the webinar on functional differential equations. As we know that many systems have the property of after effect. It means the future states depends not only on the present but also on the past history. After effect is believed to occur in mechanics, control theory, physics, chemistry, biology, medicine, economics, information theory, etc. The wide appearance of after effect is reason to regard it as a universal property of surrounding world. And if we combine the notions of differential and functional equations, we obtain the notion of functional differential equation. The coronavirus pandemic is a recent example of functional differential equations. Functional differential equations play a very important role in science and engineering, and my dear participants, you will know more about it from world-renowned mathematician Professor Jacqueline Godoy Mesquita, Department of Mathematics, University of Brasilia, Brazil, who will deliver a talk on functional differential equations, an overview and recent results. I am personally very thankful and grateful to Professor Jacqueline for accepting our invitation on such a short notice and sparing her valuable time with us. Now I invite Director Professor Lalita Ledwani, School of Basic Sciences. Over to you, ma'am.
Thank you, Dr. Giriraj. The speaker of today's event, Dr. Jacqueline Godoy Mesquita from University of Brasilia, Dean Faculty of Science, Professor Anup Kumar Mukhopadhyay, Head of Mathematics Department, Manipal University, Jaipur, Dr. Kalpana Sharma, convener of this webinar, Dr. Giriraj Methi and Dr. Sumit Srivastava, faculty members, participants from various institutions, ladies and gentlemen, a very warm greetings on this occasion, and I'm grateful to speaker of this event, Dr. Jacqueline, for giving her consent to share some of the thoughts on very important theme as mentioned by Dr. Giriraj, that it is the need of the hour to deliberate upon this particular theme, and in this pandemic situation we have further realized the importance of this particular theme. Thank you so much, madam, for your valuable time and sharing your thoughts in this webinar, and we would certainly be beneficial from knowledge that would be shared from your end. Thank you so much. I would also wish to thank Mathematics Department, especially Dr. Kalpana, Dr. Giriraj and Dr. Sumit Srivastava, who is also Controller of Examination at Manipal University, Jaipur, for taking this initiative to conduct this webinar. I am also thankful to all participants for showing their interest and showing means they are keen to attend this particular webinar. So I'm thankful to all participants. Last but not the least, I am thankful to Professor Anup Kumar Mukhopadhyay for his constant encouragement and support, not only in the conduction of this particular webinar, but we have observed that since March 2020, a series of webinars are being conducted by our different departments at the School of Basic Sciences. So thank you so much, sir, for your support, encouragement that is very much needed for the conduction of similar such academic events. I would like to take this opportunity to share some of the highlights of the School of Basic Sciences. The organizing department is one of the important constituents of the School of Basic Sciences, and School of Basic Sciences has started its functioning since the inception of the Manipal University, Jaipur, that is in the year 2011. The school operates through 5 departments that are Department of Biosciences, Chemistry, Computer Applications, Department of Mathematics and Stats, and Department of Physics. different academic programs such as BSc Honours in different disciplines, BCA, and at PG level MSc and MCA programs are being offered by the school, and PhD program is of course one such program at university level where faculty and departments are actively engaged in. And we all are aware that in current situation, the activities which are imparting knowledge not only in teaching front but also in research front in different areas that plays a very important role. So I'm very pleased to mention that our faculty members and research scholars are actively engaged in different activities, and that can further be endorsed by a number of publications in high quality peer reviewed journal. So in last 4-5 years, more than 350 publications are being produced by our faculty members, and in 2019 itself 131 publications are being produced, and in 2020 this number has even crossed that figure. And if you look at the external funding which is being fetched by our faculty members and research scholars from various government and private funding agencies, not only at national level but international level, it is gradually increasing, and more than 3.5 crore Indian rupees are being fetched by our faculty members to work on various research projects, and these days we are focusing how to bridge that gap which is there in conversion of basic and applied research to product development. So to fulfill that, our faculty members and students are oriented towards entrepreneurship skills, also development of entrepreneurship skills, and in short span 2 startups are also initiated by our faculty members. So on all fronts we have attempted our efforts, and our aim is not only to work on multidisciplinary projects but also to overcome this gap which is there between academics and industry. So with that aim we are working, and different academic programs, and of course since March 2020 all academic programs are being organized using this virtual forum, and we are very fortunate to have speakers like Madam. We are actually using this platform for important teaching and research enhancement, means skill enhancements. So academic programs conduction pace has increased tremendously, and virtual platforms are helping us a lot. So we are trying to put in all efforts with the help and support from more than 65 faculty members in the school, who are the main driving force in our school. So I'm thankful to all the students, research scholars for their active participation in all teaching and research activities, and not but the least, all participants who are attending this particular workshop. I hope the proceedings of this workshop would be extremely beneficial for everybody. And thanks once again to Dr. Jacqueline for her time. This journey of 1.5 hours or so would be extremely knowledge gaining journey. Thank you so much. Stay safe. Bye-bye.
Thank you, madam. Now I invite Dr. Kalpana Sharma to tell something about mathematics department.
Thank you, Dr. Giriraj. A very good afternoon. Professor Jacqueline from University of Brasilia, Brazil, speaker of today's webinar, Chairman Professor Ramnarayan, President Professor G.K. Prabhu, Pro-President Professor N.N. Sharma, Registrar Professor H.S. Kamath, Dean Faculty of Science Professor Anup Mukhopadhyay, Director Professor Lalita Ledwani, Deans and Directors of other faculties, HODs, faculty members from different departments, and most importantly, dear participants. It's a great pleasure indeed for me to welcome you all in this webinar on functional differential equations. Functional differential equations plays an important role in the modeling of many mechanical and electrical systems. They are also of importance in the areas of biomedical modeling, of physiological and hormonal control systems. I hope that this webinar will give you an additional insight about the given theme. I also want to take this opportunity to brief you about the Department of Mathematics and Statistics. Department of Mathematics and Statistics established in 2011 with the objective of offering world-class education and good research environment. At present, we are having 3 programs: BSc Honours Mathematics, MSc in Mathematics, and PhD program in different areas of pure and applied mathematics and statistics. The department strives for balance between teaching, research, and student development. We have qualified and committed 23 faculty members who help us to provide quality education to promote research activities in core and allied areas of mathematics and statistics. The department enables students to excel in the areas of pure as well as applied mathematics and statistics. And I hope that this webinar will be beneficial for all the students, all the research scholars who will be participating in this webinar. And once again, I extend a very warm welcome to Professor Jacqueline, and I'm thankful to you for providing your time for this webinar. And thank you very much to all the participants. Wish you a very happy learning. Thank you. Over to Dr. Giriraj.
Okay, thank you, madam. Now it is my honor and privilege to share with you a brief introduction of today's speaker, Professor Jacqueline Godoy Mesquita. Professor Jacqueline Godoy Mesquita is one of the renowned mathematicians in the world. Presently, she is working in the Department of Mathematics at University of Brasilia, Brazil. Professor Jacqueline completed her PhD in mathematics in 2012 at the University of Sao Paulo with a period at the Academy of Sciences, Czech Republic in Prague. Professor Jacqueline had 2 postdoc positions, one at the University of Santiago de Chile and the other one at the University of Sao Paulo. Professor Jacqueline has won International Bernd Alberg Prize for Students in 2012, awarded by International Society of Difference Equations. Professor Jacqueline was selected to participate at the 5th Heidelberg Forum 2017 and was selected to be Overwolfach during 2018. Professor Jacqueline was elected Young Affiliated Member of TWAS LICREP 2018 to 2022 and Affiliated Member of the Brazilian Academy of Sciences 2018 to 2022. And the Regional Secretary of Brazilian Mathematical Society 2019 to 2021. Professor Jacqueline is currently Alexander Humboldt Fellow at Justus Liebe University, Gießen, Germany. Professor Jacqueline won the Prize for Women in Sciences awarded by L'Oreal UNESCO and Brazilian Academy of Sciences in 2019 at the category of mathematics. We welcome you, madam. Today she will deliver a talk on functional differential equation, an overview and recent results. Participants, if you have questions, kindly write to them in the chat box only. We will pick them at the end of the talk. Further, we will share feedback link at the end of the program. Now over to Professor Jacqueline, madam.
Thank you very much. At first, I'd like to thank the kind introduction. Thank for that. Also thank for kind words from all of you. It's a great pleasure to me to be here and to talk about functional differential equations. I would like to thank Professor Giriraj for this invitation. It's a great pleasure to me. So I will start giving you my greetings from Brasilia. Here is my city. So you can see it's a very famous place here in my city, in my country. And also it's a view from the above of the Brasilia. So I hope that when that pandemic is finished, you can come to Brazil and to visit Brasilia. It will be my pleasure to receive you here. So the outline of my talk, I will start talking about functional differential equations, and I will give you some motivation to the study of these equations. I know that in the introduction, They also talked a lot about some applications of these equations, but also here I will bring other types of motivations, and I will talk also about the timeline of the study of these equations. So how that starts the study of functional differential equations and what was the motivation for the beginning. Then I will talk a little about some overview types of functional differential equations that we can have. And then I will talk about recent and open results in the area. So, functional differential equations. So when we try to back in the past and try to understand when the beginning of the studies of functional differential equations started, we can see the manuscript of Marquis of Condorcet. He was studying some partial differential equations, and doing some calculation, he arrived in some difference equations. So it was the beginning of the contact with this type of equations. Then later we have Poisson, and Poisson in this manuscript, he started to talk about difference equations, and more than that, talked about the importance of state-dependent delays in order to describe many types of phenomena. Then later we have Picard, and Picard, he was a plenary speaker at the International Congress of Mathematicians in 1908, and in that plenary talk, he talked about the importance to considering delay effects. So he started to talk about the importance to investigate the effects that the delay has in the solution in the future. And it was one year later that we have the first model that started to bring delays in the equation. So here you can see it's a type of a cable car. So this scientist was trying to understand the behavior and try to construct some model for that. And here he introduced a model that involves the delay. More than that, it also involves the derivative in the part of the delay. That's a type of neutral equation. And the date of that, it was in the year of 1909. So later, we have that Vito Volterra also started to talk about the importance of considering the delay effects in the phenomena, in the models. And here we have some citation of him. So he said, in all biological phenomena, it's necessary to examine not only immediate actions, but also those depending on the past. That is, on the changes which the species have undergone. These actions were first called hereditary actions, but this name was not well chosen. It was found preferable to use the term historical actions or actions belonging to memory. So in that moment, we have that Voltaire started to realize that when you deal with biological phenomena, it's very important to considering the actions, those depending on the past. So the influence of the past in order to describe and in order to understand the biological phenomena. So I will start with some motivation, and the biggest motivation for the beginning of the study of functional differential equations came from population models. So I will start to talking about the advance, the developing of the population models, and how the delay started to be considered in this type of models. So when we do some overview about population models, we have one of the first to start the study of population models was John Grant. John Grant, he collected many data about birth and death rates, and he put that in one manuscript. And later we know about Thomas Malthus, that's very famous, and he published a manuscript also saying about the growth of the population. And in that moment he stated that the growth of the population would be exponentially. And in that moment, all the people were very worried about that because he mentioned that the population growth would be exponentially and the source growth would be, the growth of sources would be arithmetically. So would be some point of the crisis. And he didn't bring any mathematical model, but since he mentioned that the growth of the population would be exponentially, we know that we can model that using this differential equation. So later we have that Verlush, he said, no, it's not like that. The population increase must be limited by the size and fertility of the country. And then Verlush proposed a very interesting model that's very famous today, that's the logistic equation. So he proposed the model that you can see here, and it's very famous among the mathematicians, since you learn this model in each course of ordinary differential equations. However, in 1948, Hudson was the first one to start to thinking about considering delay effect in the population model. So he realized that the process of reproduction is not instantaneous. So when the person was born, we know that there is some time in between to start to be able to reproduce. So he realized that, and he considered this delay term here. So he take the logistic equation and he put the delay term here in the equation. And maybe you can see and think, oh, okay, but he only put this small delay here. I don't think that it will change a lot. However, this small delay affects a lot the behavior of the solution. So here you can see that's the behavior of the solution of the logistic equation, and that's the behavior of the solution of Hudson equation. So we can see that the behavior of them are completely different. And when Hudson introduced this delay, it was very nice because there were many populations that had that oscillatory behavior. However, with the logistic equation was not able to predict this behavior, since you can see that's not oscillatory. So Hudson started to improve this type of the population models. However, if we come back here in the Hudson equation, we can see that Hudson made one mistake. He put the delay term in the death rate, not in the birth rate, what he would like, since he would like to interpret it, the delay, as the time between the birth of the person and the time that the person entered in the maturation process. So because of that, he needed to consider this delay in this part, not here. So Hudson, he realized that, and he proposed a change in the Hudson equation and putting the delay in the birth rate, not in the death rate. Also later, we have Perez, Malta, and Coutinho, and then they also investigated deeper this model and doing some experiments, and also using the equation with the delay here in the birth part, in the birth rate, not in the death rate, as it was in the time of Hudson. And here you can see the behavior of the solution. So here, if you consider the delay equal to, you have this type of behavior. If you consider the delay equal 6, you have this other type of behavior. However, later, many scientists started to realize that constant delays was not so realistic. in order to be more precise, you need to consider not constant delay, but state-dependent delays. And here I bring the citation from these three authors about that. So they were studying about population model, and here they bring some reasons to consider state-dependent delays instead of constant delays. So they mention it was observed that for Antarctic whale and seal populations, the length of time to maturity is a function of the amount of food, mostly krill, available. Prior to the Second World War, it was observed that individual seals took 5 years to mature, small whales took 7 to 10 years, and large whales species took 12 to 15 years to reach maturity. Subsequent to the introduction of factory ships after the war, and with it a depletion of the large whale populations, there was an increase in the krill available for the seals and the remaining whales. It was then noted that seals took 3 to 4 years to mature, and the small whales now only took 5 years. So we can see here that this delay will change. It's not constant, and it will depend on the state. So here they improve the population models, but in this state-dependent delay. So here is the model that they propose. And if you see, this model is the same as before with this change about the delay. Here you have state-dependent delay, and there you have constant delays. So here, if you do some change of variables, if you recall as b of y, this function here, and mu as this one, we can rewrite that model like that. And here this tau tilde is this delay depend on the states. And then we have the same type of the Blow-File equation that we had before. So here we can see the behavior of the solution when we consider state-dependent delay. Here considering that belonging in that compact interval. So we have again, it's very oscillatory behavior. Also, if you would like to compare that with constant delay, we can see in that case, we do not have a big difference between them. However, we know that depending on the equation and depending on the model, we can have a big difference between state-dependent delay equations behavior and constant delays. Here it's not so big difference as you can see. However, you can have a big difference depending on the model. Also, Arina et al., they also mention about the importance to consider state-dependent delay when you study population models. So they mention, in the context of population dynamics, the delay arises frequently as the maturation time from birth to adulthood. And this time is in some cases a function of the total population. So also he realized the importance to consider the state-dependent delays when you deal with population models. So let's see now some types of functional differential equations. We can have many types of functional differential equations, and I will try to talk about all these types that we have. So here we have, we'll start with bounded delays. So here we have this type of functional differential equations, and we use that notation here in blue to mention that it's a function of theta. So x of t, you apply for theta in theta, and it's equal x of t plus theta, where theta belongs to this compact interval, since you are dealing here with bounded delays. And here the initial condition is a function. So it's not like in an ODE that you know what happens in t0 only, but here you know what happens in some interval. So you know a little about the memory of the function. So here is the initial condition described by a function. Also, we can have the time-dependent delays. So instead of considering only t here, you can consider here r of t. That's a function of t. And if you have that function is equal the identity, you have the previous case. However, you could have that this one is any function that you want. So you have here these functional differential equations with time-dependent delays. And again, it's given by this. And here we are considering bounded delay. So we have that theta belongs here to that compact interval. Also, we can have the state-dependent delays. So it's given by this here. So this whole depends on the state. So we have this type. And here is the definition for theta here in that compact intervals. Also, we can have unbounded delays. So here in that case, our theta belongs to unbounded intervals. Also here for time-dependent delays, for state-dependent delays, it's important to mention that when we deal with unbounded delays, we need to be careful because we need to consider appropriate phase space in order to our function, our solution be well defined. So here we have some difficulties in order to have unbounded delays. Also here we have functional differential equations which is given by these, but also we can have neutral equations. These neutral equations is that when we have the derivative in the delay part. So here we need to have another term in the f, which means that is a part with delay and with the derivative. When we have this type of equation, we call that as a neutral equation. So we can have the neutral functional differential equations with time-dependent delays if the derivative appears with the time-dependent delays. Also, we can have the neutral functional differential equations with state-dependent delay, again, when the derivative appears in the part with state-dependent delays. So when we have these things, we have this other type of equations, that's the neutral, and they are very important also for applications. So the equations with state-dependent delays, they have a lot of applications. However, they were a long time without being studied a lot. And then with the work about Driver proposed the two-body problem of electrodynamics, and in his model he considered state-dependent delay. More precisely, he considered the neutral functional differential equations with state-dependent delays. And he realized that the way to have a precise description of two-body problems in electrodynamics, he needed to consider state-dependent delays. And differently that we had in the past, because in the past the two-body problems in mechanical celeste that it was considered by Poincaré, it was considered without considering delay. However, in electrodynamics, the situation is different, and Driver brings a very important motivation to study this type of problem using state-dependent delay equations. However, these equations, they have a lot of applications, but they are very hard to deal with. And here I bring the citation of Hans Otto Walther that he mentioned about that. He says, state-dependent delays arise in various circumstances, but it seems not obvious how to single out a tractable class of equations which contains a large set of examples which are well motivated. So we have a lot of applications of these equations. However, to deal with them, it's very hard. So we really need to investigate it, appropriate spaces, about regularity. So we have a lot of difficulties in deal directly with them. So also here, I bring some motivations about some applications that also were mentioned in the beginning of this talk, in the introduction. That's about the disease. We know that there are some disease with incubation periods. That's the case of COVID-19, Zika, dengue, and other disease. The person that is infected does not present the symptoms instantaneously. We know that it takes time between the person being infected and the symptoms start to appear. And that's why this type of equations, functional differential equations, considering delay, it's so important to describe this type of disease with this incubation period. Also, it's important to consider that this delay is not constant. We know that it depends. It can take some time, in some range, some interval, and it can vary from person to person. So it's very important to consider not only functional differential equations, but functional differential equations with no constant delays in that case. So now I will talk a little about some recent results in that area. So one type of equations that started to be very well studied is about measure functional differential equations, which is a little more general than functional differential equations. So a measure functional differential equations has the following integral form that you can see here. And if you realize here, if our G is the identity, we have that this one is exactly the functional differential equation that we had before. Here, for that y of s, that's a function of theta. So here we are not considering the time-dependent delay or state-dependent delay. So here it's simple one with functional differential equations. And then here also we are considering the bounded delays. So here the delays in the compact interval. So here we have these measure functional differential equations. And these type of equations are more general than functional differential equation. As you can see, if the G is the identity, we have the functional differential equations. However, we can have much more types of equations inside of these measure functional differential equations. Also here, our solutions can be discontinuous. If you see, if our function G is discontinuous function, so the solution is also discontinuous. So here we can have a more general consideration of for models and so on. Also, it's possible to relate measure functional differential equations with other types of equations. And that's why these equations are so interesting to deal. So I will start talking the relation between measure functional differential equations and measure functional differential equations with impulses. So here we have measure functional differential equations with impulses. So here we have the description of the measured functional differential equations, and then here you have the impulsive behavior, and then here the initial condition. And then if we assume that our G is a left continuous function which is continuous at the moment of impulses, then we have that this integral here is continuous at the moment of impulses, which means that this integral does not jump at the same time as the impulses operators. So we can rewrite our problem in this integral form here, and here with this initial condition. And then we can have a relation between these two types of equations. So if we define f tilde equal f in all the interval except in the moments of impulses, and if we define this one equal the impulses operators in the moment of impulses, and define our d tilde equal g except by a constant in these intervals, then we will have that X is a solution of measure functional differential equations with impulses if and only if X is a solution of measure functional differential equations, which means that with this type of correspondence, we can prove a result for measure functional differential equation, and as a particular case, we have a result for measure functional differential equations with impulses. So we have a result for these equations only using the results for measure functional differential equations. Also here, if you have a look here, if you consider G equal the identity, you have here the impulsive functional differential equations. So again, these type of equations can also include this type of equations inside of that. Also, it's possible to relate measure functional differential equations with other type of equations called functional dynamic equations on time scales. So, before to talk about that type of correspondence, I will give a very brief overview about timescale theory. So, the timescale theory is very recent theory. It was introduced in 1988 by Stephen Hilger in his PhD thesis. So Stephen Hilger, in his PhD thesis, he would like to unify discrete and continuous case. He would like to create a theory that he could prove a result just once and has as a consequence the result for the continuous, which means for differential equations, and also to have the result for the integers, for the discrete case, for the difference equations. And he created a theory that could unify not only these two cases, but much more than that. So a time scales is only a closed and no empty subset of the real numbers, which means that we can have several examples of time scales. So we can, with this theory, unify discrete and continuous case. We can unify other cases depending on the chosen time scales. As I mentioned before, a time scale is only a closed and no empty subset of the real numbers. So we can have several examples, such as Cantor set is a type of time scales. So we can have many examples. And because of that, we can have many types of applications for that theory. So here I cite this paper that brings an application of time scales to economic models. So in that paper, they study such a type of consumption model, and they investigate that in the framework of continuous time, discrete time, and time scale times. And when they consider time scale, they can predict much more situations because of we can have hybrid situations, we can have discrete, continuous, all the types of time that we want using time scales. Also, it plays an important role for applications in population models. In that book, we can see a theory of population in biological communities that consider many different population of insects that can be described using different time scales. Also, we have some population which have some period of hibernation, and this type of population can be described using timescale theory. You can consider like a union of closed intervals, and you can consider that population behavior continuously in the interval, and then when you have that gap, you can consider that as a hibernation period, and then you can consider again as continuous and then hibernation and so on. So also we have a lot of application for population models. So since you would like to have a relation between this functional dynamic equation timescales and measure equations, we need to relate the integral equations between them. So the delta integrals, which comes from the timescale theory, and Still's integrals that comes from measure differential equations. So we would like to construct a bridge between them. However, in order to construct this bridge, we need to pay attention that when we deal with timescales, we can have some holes in our domain. When we deal with Z, for instance, we have some holes in our domain. We do not have that continuously. However, when you deal with Still's integral measure equations, we have the solutions defined in all the interval. So in order to have the bridge between both theories, we needed to introduce some ways in order to overlap these holes of the timescale theory and relate both. So that's why we define this operator star here. So we have that if T belongs to the real number set and is such that this is more or equal the supremo of the timescales here, this is the notation for the timescales. So we have that T star given by this infimo here, it will be our operator that we use it to overlap these holes. And then we define the extension of the timescales by this timescales star that's given by the minus infinity until the supremo of the timescales if the supremo is finite, and it will be the real line if we have the supremo is infinity. So given a function f, we can define it now using that operator star, the extension of this function. So this function is defined on the timescales, and that this extension is defined in that extension of the timescales that's denoted by the timescales star. And we define that like f star t is equal ft star. And so here we can see the example. So here we have the function f defined on the timescales. So we have these holes here because of the domain of the timescales. And the f star, we can cover all these holes by the definition. So we can have this relation between f and f star. So f star is a type of extension of the function f. So using that, we can relate the delta integral that appears in the theory of the timescales and the Still's integral. So we have a relation between this type of delta integrals and here the Still's integral. So we know that if we define our G equal S star for all S in the extension of the timescales, then we have that this function F2 is equal F1 star. So we have a relation between both. And using that relation, we can have a relation between the functional dynamic equation on timescales and measure functional differential equation. So here we have that X is a solution of functional dynamic equation on timescales given by this. So here is the delta integral in the sense of this theory of timescale. And then if we have that X is a solution of that, we have that extension of that X, which means X star, is a solution of measure functional differential equation given by this. And then if Y satisfies 3, then we have that Y has the form X star, where X is a solution of functional dynamic equation timescales. So here we have that we can put inside of measure functional differential equation, we can put many types of equations. So we can put functional differential equations with impulses, as we saw before. We can have inside of functional differential equations with impulses, functional differential equations. And also we can put inside of measure functional differential equations, functional dynamic equation timescales, functional differential equations, ODEs, and so we can put inside of this big set of measure functional differential equations many types of equations. And that's why this type of equations are so interesting to deal, because we can prove a result for measured functional differential equation, and then we can translate it to all these types of equations. And also, more than that, the other motivation to deal with this type of equations is because since, as we saw before, the solution of measured functional differential equations does not to be continuous, so they can be discontinuous. So the hypotheses concerning the function that we deal with measured functional differential equations are more general than the usual. So we put a more flexible type of conditions. So more general types of Lipschitz conditions, more general types of boundless conditions we can put in these types of equations. So here let's see some applications of this correspondence of these types of equations. So we prove some results concerning averaging principles. So we prove non-periodic averaging principle for these types of equations, for measured functional differential equations, and then pass these results to other types of equations. Also periodic averaging principle for various types of equations. Also prolongation of solutions, we prove for these types of equations and then pass to other types of equations. Stability results using Lyapunov functional, prove for this equation, then pass it to other types of equations by these types of relations. Also boundness of solution using Lyapunov functionals. Growth of solution, again, also to this equation and pass to other types of equations. And it's important to mention that when we translate all these results, we have more general results for our equations. So it usually generalizes the results that we have for functional differential equations, for functional differential equations with impulses, and so on. So I choose here one of that applications only to talk a little more about, and I choose averaging principles. So there are two types of averaging principles, the periodic averaging principles and non-periodic averaging principles. So let's start with periodic averaging principles. So I will very quickly recall the periodicity definition. So we say that a function f is t periodic if we have that this relation here is satisfied, for all t in R. Also, we say that the function is called t periodic with respect to the second variable if we have this equality holds. Then using that, we can explain about periodic averaging methods. So the periodic averaging method, it says that if you have here this original equation, it's possible to define, if you have that your f is t periodic concerning the second variable here, we can define our f0 by this expression here, where t is the period of our function f, and using that we can construct the averaged equation given by this, and the periodic averaging principle, it ensures that the solution of the original equation is very close of the solution of the average equation. So we have this relation between them. So it's very nice theorem because we can ensure, we can study the solution of the original equation only knowing the solution of the averaged equation. And this type of equation is much more simple to deal than this one, since here we have autonomous equation. So we can investigate it here, the asymptotic behavior of the solution, if it's stable, if it's unstable, about bifurcation, oscillation, only knowing the solution of the averaged equation. So here are some examples. So here we have this original equation, and using that formula, we can calculate the averaged equation. And if you plot them, here in blue is the original solution, and here in red is the solution of the averaged equation. So we can see that both are very close from each other. Also here, considering delay, we have this, the original equation. Here is the averaged equation. And then if we plot them, we can see that they are very close from each other. Also about non-periodic averaging principles. Here we have the original equation, but now our function f is not longer a periodic function. But even in that case, we can have the non-periodic averaging methods. So if we define our f0 equal that limit, and if this limit exists, so we can define our averaged equation given by this. And again, we have that the solution of the original equation will be very close to the solution of the averaged equation in our non-periodic averaging methods. And here we have this type of example. Here we have the original equation, and then we can calculate it, the averaged equation. And if we plot, then we can see that we have in the very large time, we have that both are very close from each other. So we can use this averaging principle to investigate it about stability, attractors, bifurcation, asymptotic behavior of the original equations, only using the averaged equations. And so in the past, the averaging principle were very important to investigate it, the two-body problems, also the three-body problems, because of this relation that we have, and we can investigate it about the solution of the original equations only using this averaged equation. Now, I would like to talk about some open and developing problems. So we have mainly actually open and developing problems, and I tried to list some of them. So measure functional differential equations with state-dependent delays. How would that be, and how the results could be in that case? When we deal with state-dependent delays, we have some problems about regularity, the spaces, so we need to be very careful in that moment. So it's a developing problem, and I'm trying to investigate it, the behavior of the solutions in that case, the phase space that I needed to consider in order to study these types of equations. Also, when we consider neutral equations, so measure neutral functional differential equations with state-dependent delays, how that would be, and also with time-dependent delays. So these are some open problems. Also about the linearized instability for neutral functional differential equations with state-dependent delays. Here we have some problems because when you deal with linearized instability for neutral equations, we have some problems in the spectrum, because here we can have that we can have eigenvalues, we can have infinite eigenvalues in the spectrum of the neutral functional differential equation. So we need to be very careful, especially about the linearized instability, in order to have some estimates about our semigroups. Also, other type of open problem is about periodic solutions for neutral functional differential equations with state-dependent delays. So these types of equations, neutral functional differential equations with state-dependent delays, they are very new in the literature, so there are a lot of open problems in that direction, including types of models to consider. Hans-Otto Walter considered occurrence exchange models for neutral functional differential equations. Also, we have the models from drivers, but also there are others that we could investigate it using these types of equations, and there are a lot of open problems in that direction to investigate it, these types of problems. So here it's a picture of all my co-authors that I would like to introduce to you. So that I wrote my works in that field. And thank you very much for your attention.
Thank you, madam, for such a knowledgeable and wonderful talk. Now, with your permission, can I ask some questions which participants have asked to you?
Yeah, sure.
Yeah. So the first question is, how we can relate initial conditions with impulse condition in the study of functional differential equations?
Okay, usually when we have the relation between measured functional differential equations and measured functional differential equations with impulses, to have the relation between them, the initial conditions are the same when we have the relation between these two types of equations. So we use the same initial condition for them.
Okay. The second question is, can delay differential equations be applied to meromorphic functions? Can you give me any references?
I don't know if it's possible, and I don't know any reference about that. Probably it's possible, but I don't know reference about that.
Okay. The third one is, what are the basic books we should study to have idea of about functional differential equations?
Yeah, there are the books from Jackie Hale and Lunel. They are the most classic books in that direction about functional differential equations. Also, there are books from Dickerman and Hans-Otto Walter that you also can see more about these functional differential equations. And also, if you'd like to come back in the past, also has the books from Bellman and Cook, also about the functional differential equations.
Okay, so last but not the least, what according to you is the good method to solve delay differential equations with multiple delays?
Well, it's difficult usually to solve explicitly any type of delay equations, but usually the method that I use is the method of steps. So I work in steps and try to see which is happening in each part. But usually it's very hard to solve directly the delay equations. So when I need to do so, I do the method of steps, or other possibilities also using these integral forms. But it's very hard usually to deal with that because you need to pay attention about these intervals, where the function is defined, and so on.
Thank you, madam. Okay, now I invite Professor Sumit Shrivastava for vote of thanks.
Thank you, sir. So on behalf of Manipal University, Jaipur, I'd like to thank, I deem it a great honor to propose the vote of thanks in making this webinar such a resounding success. First of all, I'd like to propose a hearty vote of thanks to our Dean, Faculty of Science, Professor Anup Mukhopadhyay, Director, School of Basic Science, Dr. Lalita Ledwani, Head, Dr. Kalpana Sharma for gracing today's webinar. Thank all of you for very interesting and thoughtful provoking at this. I would like to thank our distinguished speaker, Professor Jacqueline, for making excellent presentation on functional differential equation and making this webinar interesting and meaningful. The listeners will definitely get an insight to the various aspects of it. I am happy to share that the webinar was watched by more than 600 participants within and outside Manipal University, Jaipur. And for this, I'd like to convey my sincere thanks to Dr. Giriraj Methi, the convener for the event, and the audience who have made this webinar a grand success. Once again, I thank all for your cordial cooperation from Manipal University, Jaipur. Thank you all.
Thank you, sir. And once again, thank you very much, madam. We really appreciate your cooperation and motivation. Thank you very much.
Thank you for this invitation. Thank you very much.
Yeah,
one more. It was a pleasure to me.
Yeah, I would also like to thank my colleague Rishikesh Rishikesh Dutt Tiwari, who really helped me in this organizing this event. Thank you, Rishikesh. Thank you, madam.
Thank you, sir.
Thank you very much.
Okay, ma'am, bye. Okay, ma'am. We will be in constant touch.
Yeah.
Yeah, for further collaboration in projects and research papers, we will be in constant touch, ma'am.
Yeah, okay, nice. Thank you very much for this invitation. It was my pleasure.
Thank you, madam. Thank you very much.
Okay, bye-bye.
Bye-bye.